This is going to be a run through of some really dumb shenanigans you can do with RabbitMQ. Specifically, I'm going to show you how you can use existing RabbitMQ features to create a type of queue that, as far as I can tell, doesn't exist anywhere else. That queue is the arbitrary time delay queue. That said, this type of queue in RabbitMQ is not perfect, and it has flaws, but it's still really cool, and we'll get to those flaws at the end. To start off with, let's do a quick rundown on what RabbitMQ is and queuing systems in general. As the name implies, queuing systems, or sometimes queuing services, such as RabbitMQ, Kafka, and Amazon's SQS, are systems/services that queue stuff up for consumption by different processes. They're basically the equivalent of a line for security at an airport. Queue systems allow the program sending and the program receiving from the queue to operate at their own pace, independent of one another, which is very powerful. The way each of the three services I mentioned earlier implements queuing is different. They all have their own quirks. The quirks of RabbitMQ, in this particular case anyway, are what allow us to make arbitrary time delay queues possible. To explain how a time delay queue works, we need to explain how RabbitMQ works, at least at a high level. The first thing to know is that messages get sent from the sending program to an exchange. The messages are then distributed by that exchange to the appropriate attached queues. Under normal circumstances, receiving programs will then consume messages from the queue, completing the delivery. Under some circumstances, however, it's possible for a message in a queue to die and end up getting what's called dead lettered. This can happen for many reasons, but the most common one is encountering an error when getting processed. Another reason a message can die, and the important one in our circumstance, is that the message can time out waiting in the queue. RabbitMQ allows different things to happen to a message that is dead lettered. This is selectable when setting up the queue. The message can be deleted, be routed to a new queue, or be routed to a new exchange. The last one is the one that we need to create the time delay and arbitrary time delay queues. The method of creating a basic time delay queue is rather simple. The sending program sends a message to exchange A, which then routes them to queue A. There's nothing processing the messages in queue A, so eventually, after a preset delay, the messages time out. Those timed out messages dead letter into exchange B, and from there, queue B, which does have something processing the messages. This chain of exchange, queue, receiving process means that the soonest messages can be processed is the length of the timeout on queue A. Unfortunately, the timeout in the queue is determined when setting up the queue. There's no way to adjust the timeout for each individual message. Thus, to delay for any given desired time, you need to set up a queue for that specific time. It's not ideal in a lot of circumstances. To solve this, we're going to use another feature of RabbitMQ queues to make it so that this time delay queue can be arbitrary. When passing a message to RabbitMQ, it's possible to set a key on that message for certain functionality. That key can be used by the processing exchange to determine what queue a message gets sent to. That key can also be wildcard matched. By abusing the wildcard matching and constructing the key and queue setup properly, it is possible to chain a series of time delay queues in exactly the order necessary to end up with any arbitrary delay. The method we are going to use is to construct a chain of queues with delays of decreasing powers of 2. Each queue will output to an exchange that then determines what queue the message goes to next by looking at the key, and from there, selecting the next desired power of 2. The way it does this is by having the key be a binary encoded representation of the desired minimum delay. Each exchange will then use multi-character wildcards to ignore all of the bits before the highest bit they care about, and then use a pattern of n 0-bit values, followed by a 1 value, followed by k minus n minus 1 single wildcard characters to determine what next queue to go to. That's a little bit complicated, so let's walk through an example. Here we have a message that just came from the 16-second queue, i.e. the 5th bit was a 1. As such, we only care about the bottom 4 bits in the message's key. From here, the message can only go to one of 5 possible places: the 8, 4, 2, and 1 second delay queues and the done queue. For the 8-second delay queue, the value of the bottom 4 bits would be a 1 followed by any 3 other values. The 4-second delay queue would be a 0 and then a 1 and then any 2 values. The 2-second delay would be 2 zeros, a 1, and then any 1 value. The 1-second delay, 3 zeros, a 1, and then there's nothing left. And then finally, if the delay is complete, the message should go to the done queue, in which case the bottom 4 bits would all be zeros. That converts to the following keys. In this table, you can see what those keys look like. In RabbitMQ, the octothorpe is the match any number of characters symbol, while the star is match a single character. This method of key generation allows connecting every queue to every other queue that has a smaller delay than that first queue. In other words, when a message has completed its delay in one queue, it will be passed off to the next queue with the highest possible delay that is less than or equal to the remaining delay on the message. If you take a look at the following diagram, you can see how different queues interact. Each queue is connected to many other queues, but only those queues with a shorter delay. As a consequence, the message will only ever be processed by the next shorter, then shorter, then shorter delay, eventually reaching the done queue. Overall, this process is really cool and allows some fun functionality. I actually use it in Streemtech to allow for rate limit backoffs without requiring the message to sit around blocking other messages from being processed. Unfortunately, it has some downsides. To start, if the RabbitMQ cluster goes offline, messages will, at most, complete one queue delay. When the cluster comes back online, the message will not automatically get passed to the next queue or the done queue if the required delay has elapsed. In cases such as these, setting a timeout on the message itself, such that the receiving process can determine if it should process the message, is strongly advised. Another issue with this method is that the required number of connections grows at a rate of about n squared over 2, where n is the number of bits in the delay. Because each queue has to connect with nearly every other queue, you can end up with hundreds or thousands of exchange queue connections. In the simple 4-bit diagram, there are 16 connections. Finally, due to the uneven length of time that the queues hold messages for, if you have an even distribution of delays, you'll have more messages in the larger delay queues at any given time. This can slow down processing in some circumstances. All of these issues combine to really encourage using this method only on shorter delays. For longer delays, you can consider using a database to store the messages, and then have a cron job or something similar that pipes the messages to the delay queue on a regular interval. For Streemtech, the longest queue delay I have is about a week, which can be represented by 20 bits, or about 250 connections, given some overhead. That's well outside of what I recommend for normal use, however, which is about an hour, requiring only 12 bits. With 16 bits, you can have about 18 hours of delay, which is realistically the maximum that I would recommend in most circumstances. The other reason that having a large delay is problematic is that setting up all of the queue connections is kind of complicated. Even a single mistake could lead to problems with certain delays. You may even have messages that loop infinitely. As such, I recommend only ever setting up this time delay queue with some kind of infrastructure as code system. At Streemtech, we use Terraform to perform this role, and the post linked in the description has a rough outline of the Terraform used. Do be warned that this Terraform is not perfect, and it's been a while since I've updated it. It should only be used as an example. Please implement this code yourself to make sure you understand enough to solve any problems you might encounter. But that's it. That is how to use RabbitMQ's keys and dead lettering to have an arbitrary time delay queue. It's a really powerful tool, and I want to see what you make of it. If you have any questions, hit me up in the comments on Blue Sky or on Mastodon. My name is Deef. Stay crazy, stay curious.